So in this video, we are going to talk about the empirical rule and introduce the idea of Z. So let's start with the empirical rule. It is also called the rule of thumb. Okay, it is also called the rule of thumb or the 68, 95, 99 rule. Okay, so in a very simple context, here is what the rule says. Okay, the basic assumption that the rule is making is that the data set that you're working with follows a normal distribution. Okay, so if you have a data set that follows a normal distribution with a mean mu and a standard deviation of sigma, whatever those values are, okay, and you take 68% of that data set centrally cut meaning you are essentially looking at this central cut, and this is 68%, which basically means this 1/2 is 34%. Okay, so if you take a data set that is normally distributed and you take 68% of the data set centrally, then when you look into these specific points, which are the two ends of that cut, this point here will be 1 sigma away from the mean. This point here will also be 1 sigma away from the mean. That's the whole idea of the empirical rule. So let's put this into a numerical example, because or else it doesn't really make too much of sense. So numerically, let's imagine that I have a data that is normally distributed with a mean of 10 and a sigma of 2. Okay, so in other words, this sigma of 2 is known to me, and because of this sigma value, this particular distribution is shaped this way. You might want to ask yourself, okay, Dr. B, what happens to this shape if this sigma becomes 4? This shape becomes much more flatter. You got that right. What happens if this sigma becomes 1? This shape becomes much more closer to the mean. That's the whole idea of sigma that we discussed in the last video. So let us imagine that you have this distribution with a mu equal 10 and sigma equals 2. Okay? According to this empirical rule, this point here is 1 sigma away from the mean. Okay? In other words, that distance from the mean is 1 sigma, and each sigma is 2 units, right? And therefore, the value at that point would be what? You already have 10 plus 1 sigma, right? Which is 10 plus 1 times 2, which is 12. So the value here becomes 12. In the same way, what would the value on this side be? It is the same exact thing, only a mirror image. It is 1 sigma away on the other side, and you guessed it right, that value is 8. Okay, 10 minus 1 sigma, or 10 minus 2, which is 8. So in other words, all you are saying is, according to this rule, if your data is centrally is normally distributed, and if you arrange that data in a certain order, so this is your data, right? This is the distribution of data that goes from a certain minimum value to a certain maximum value. If you pinpoint the value 8 on the data set and the value 12 on the data set, and you take all the data points on that data set between 8 and 12, you capture 68% of the data. That's basically what this rule is telling you. So in that same vein, if I basically go ahead and draw the 95% rule, so for the 95%, all I'm saying is the same exact story. I have a distribution with a mean mu and a standard deviation sigma. If I take 95% of that data centrally cut, 95% of that data centrally cut, then when I'm looking at these two edges or cut points, this one is 2 sigma away. This one is also 2 sigma away from the mean. Okay, in other words, if I take a cross section of this data set, centrally cut 95%, my two ends will be 2 sigma away from the mean. So we can actually apply the same concept here that we applied in the 68%. Okay, so if I one more time imagine that my mu is 10, my sigma is 2. So this guy here turns out to be 10 plus 2 sigma, right, which is 10 plus 2 times 2, which is 10 plus 4, which is 14. So the value here is 14. In the same way, the value here is a mirror image. It's 2 sigma away on the other side, so it's 10 minus 2 sigma. Each sigma is 2 units, so it's 10 minus 4, which is 6. So if you really compare the 68 and the 95 rule, it's an intuitive understanding that initially you were looking at the data points between 8 and 12, and that's only 68%. If you increase it on both ends, you are now looking at the data points from 6 till 14. And now you have much more data that has been captured herein. That's your idea of 95%. Okay, so between 6 and 14, 95% of the data set is captured. That's basically what this rule is saying. And so, last but not the least, if I am looking at the third piece of the puzzle, which is 99% or almost the entire data set. Okay, so again, the underlying assumption is that the data follows a normal distribution. And with a mu of mu and a sigma, and if I am capturing 99% or almost the entire data set here, so this is 99%. If I'm able to capture almost the entire data set here, these two ends that you see, this guy here would be 3 sigma away. This guy here will be 3 sigma away. And the rest is absolute routine work. So I one more time put some values here. Imagine that my mu is still 10, my sigma is 2, and so what turns out is this point here, which is as close as possible to the maximum value, because 99% is almost the entire data set. Okay, this is 3 sigma away, and so the value here would be 10 plus 3 sigma, which is 10 plus 3 times 2, which is 16. Okay, so this value here is 16. In the very same way, this value here is 3 sigma away on the other side. Each sigma is 2 units, so essentially it's 3 times 2 or 6 units away. This value here is 4. So again, if you look at the progression, between 8 and 12, you are able to capture 68% of the data. Between 6 and 14, you are able to capture 95% of the data. Between 4 and 16, you are able to capture 99% or almost the entire data set. That is the intuitive approach to understanding the empirical rule. So far, so good, right? So the problem with the empirical rule is in this data set, if I ask you how many points on this plane can you identify in terms of what their values are? Okay, your correct answer should be 7 because you're able to identify this guy, this guy, this guy, this guy, this guy, this guy, and of course your mean. Okay, so 8, 12, 6, 14, 4, 16, and the mean. That's only 7 points on the data set. And you can very closely identify those 7-point values based on the empirical rule. What about the remaining points? What about the idea of a continuous distribution, which basically means that the data, there can be an infinite number of possible values on this plane. And of these infinite possible values, I am able to capture only 7 of those. How do I go about capturing the remaining? Is there a generic rule that I can use to capture the rest? And that's where the idea of Z comes. Okay, so the idea of Z is very simple. I'm going past the empirical rule. I'm of course going to use the concepts there and saying, let us suppose I have a data that is normally distributed. So again, I'm making that assumption of normal distribution with a mean mu and a standard deviation of sigma. And there is a certain point on that distribution, any point, I don't care where you want to make that point. And let's suppose that point value is x. Can I make a general form or a generic form of x based off of what I have seen so far here? And I'm going to give you a hint. There is a certain pattern in the process. You see this point 12? Recall how we got that point. It's 1 sigma away from the mean, right? And so to be able to capture that point, we were able to take the sigma, take the mean and add 1 sigma to it. It's 10 plus 1 sigma. Now let's look at this point 14. How did we capture that? It's 2 sigma away from the mean. So essentially, you took the mean of 10 and added 2 sigma to it. Look at this point 16. How did we capture that? It is 3 sigma away from the mean. Okay, and so that's basically what you have done. Mean plus 3 sigma. Now I want you guys to take a step back and look at those 3 rectangular brackets that I have created. 10 plus 1 sigma, 10 plus 2 sigma, 10 plus 3 sigma, where 10 is the same as you are seeing. So this is where 10 is the mean that is the same across the board. You are adding to the mean because you are trying to see how far it is away from the mean. Okay, so that is basically defining how far it is away from the mean. And then you're adding a certain factor to sigma. It's either 1 sigma, 2 sigma, or 3 sigma away from the mean, right? That's how the empirical rule has been set up. So in our case, we will set this up in the very simple form. This is x that we are trying to measure. And we know that it is a certain number of standard deviations away from the mean. Only in this case, when we are trying to generalize it, we don't know how many standard deviations it is away. Okay, but we know that it is mu plus a certain number of standard deviations away. I just don't know what that number is. 1, 2, 3. How do I generalize that? Okay, and so what happened is the mathematician, and this gentleman is oftentimes called the father of modern statistics. His name is Fisher. You have actually come across him when you studied ANOVA with Dr. Lamb in the F test of ANOVA. That F test is named after Fisher. So he came up with a variable name called Z. And he said any point x on the distribution is Z standard deviations away from the mean. So those 1, 2, and 3 that you are seeing here, they're all possible variables. he generalized them into a variable called z. And I'm saying this again, follow along with how I'm circling it as I say it. Any point x on the distribution is z standard deviations away from the mean. I write it again. Any point x on a distribution is z standard deviations away from the mean. That's basically the way you represent z. So my friends, what does z mean? Z is a measure of what? Z is a measure of the number of standard deviations that a certain point x is away from the mean. How many standard deviations is that point away? Going back to here, this point 16 is 3 standard deviations away from the mean. So if I ask you, what is the z value here? You got that right? It's 3. 3 is the z value for that point. What is the z value here? For 14. How far is 14 away from the mean? It's 2 standard deviations away. So the z value, by the very basic definition of z, the z value is 2. What is the corresponding z value of 12? It's 1. What would then be the corresponding z value of 8? Because 8 is just on the other side, it's a mirror image. That z value would be negative 1. This one would be negative 2. For this guy. For this guy, the z value would be negative 3. So if you really look at the empirical rule, in essence, your z takes a value between positive 3 and negative 3 by the pure definition of the empirical rule. If you open up your z table, you'll see that it takes a value that is a little more than 3 or a little less than negative 3. That's why the empirical rule is a rule of thumb. It is a very close estimate. I call it a smell test because it does wonders understanding the bigger picture without getting into the details of the statistics. So the other thing that you would want to remember is the idea of z is so central to the understanding of statistics because z has the capability of standardizing any normal distribution. So I can start off with a normal distribution that is representing any data set, and I can do its corresponding z distribution that takes a value roughly between positive 3 and negative 3 if you are looking into a 99% cut of the data set. But more importantly, going by the definition of z, one more time, z represents the number of standard deviations that a point is away from the mean. So if I look at this point, which is the mean itself, and I ask you, what would the corresponding z value be for this point, for the mean? Again, z represents what? The number of standard deviations that a point is away from the mean. If it is on the mean itself, is it away from the mean? No. So the z value for it is, you guessed it right. If this is mean, the corresponding z value is always 0. And here lies the beauty of z. You bring in any data set, be it your grades, be it the time it takes to serve customers, be it the salaries, be it revenue, be it stock prices, you bring it on. And if you convert that into a corresponding z distribution, it is always centered around 0. Always, always, always. That makes the z distribution a standard normal distribution because it standardizes any normal distribution. And so that is what I have written up here in this slide. Any normal distributed variable y with a mean mu and a standard deviation sigma can be transformed into the standard normal variable z using the following. One, any value y on the normal distribution, and I call this y, you can call this x, it doesn't really matter. Okay, is z standard deviations away from the mean. So mathematically, your x or y is mu plus z sigma. Okay, so on that same token, if you rearrange this, you can say x minus mu, right, equals z sigma, or sigma equals x minus mu over z. You can also say from here that z equals x minus mu over sigma. So you can do very basic mathematical substitutions to gather to this point. Okay, z is the number of standard deviations between y and its mean, or in this case between x and its mean. Okay, number of standard deviations. So you divide that difference by sigma, and that is what you get in terms of z. Okay, and it's the same idea whether it's y or x, it doesn't really matter. So z can take values from -3 to +3, and this is primarily based on the empirical rule. It can take values a slight more than 3 and a slight less than 3 if you open up a real z table. Okay. So in the next video, we will look at some concrete examples of how the z can be applied, and then we'll look into reading the z tables and also looking into Excel.